Okay, picture this for a second. A leafcutter ant colony. You've got millions of ants, right? No boss ant, no central plan.
Uh-huh. Just following simple rules.
Exactly. Simple rules, but they create these incredibly complex societies, massive underground cities. They even farm their own food. It's like decentralized complexity.
That's a great analogy, actually, because Bitcoin, in a way, is quite similar.
Right. No CEO, no central bank, but it moves billions around the globe securely every single day. So, okay, let's try and unpack that.
Let's do it.
For you today, we're going deep. We want to get past the price speculation and all that noise.
Yeah, the hype.
Our mission here is to pull out the core ideas, those moments where it just clicks so you can really understand how this whole internet of money actually functions.
And a really fantastic guide for this is Mastering Bitcoin by Andreas and Antonopoulos. It's perfect for understanding the mechanics without needing to be a coder.
Definitely. It's our main source for this deep dive.
So we'll be leaning on that quite a bit as we navigate through this.
Exactly. And the goal is real understanding, not just getting buried in jargon. We'll look at how transactions work, how mining and the blockchain keep things secure, and even some, well, surprising uses beyond just money. Ready?
Absolutely. Let's start at the beginning. A basic Bitcoin transaction. How does value actually move?
Okay, so fundamentally, a transaction is just a record, right? Saying value moved from owner A to owner B.
Digitally, yeah. It's like a chain of ownership, cryptographically secured.
And when a transaction happens, you hear about inputs and outputs. What are those exactly?
Right. So the inputs are like the debits. They point to specific chunks of Bitcoin you received previously that haven't been spent yet. We call those UTXOs, unspent transaction outputs.
UTXOs. Got it. Like specific coins you own.
Kind of, yeah. Your wallet picks which UTXOs to use. The outputs then are the credits. They say, okay, send this amount of Bitcoin to this specific address.
Makes sense. Inputs are where the money comes from. Outputs are where it's going.
Exactly. And here's a key thing. The total value of the inputs might be more than the total value of the outputs going to the recipient.
Uh-huh. Where does the extra go?
That difference, usually a small amount, is the transaction fee.
Okay. That's for the miners, the people processing everything.
Precisely. It's their incentive to grab your transaction and include it in the official record, the blockchain. Think of it like balancing a ledger. Inputs have to equal outputs plus the fee.
Okay, let's make this concrete. Say Joe sent Alice 0.10 Bitcoin sometime back.
Right. Her wallet probably showed her the equivalent in, say, dollars or euros at the time. Now, Alice wants to buy coffee from Bob. Costs 0.1 BCC.
So she uses that 0.10 BTC she got from Joe.
Yep, that UTXO becomes an input. One output will be 0.01 BTC going to Bob's address. And crucially, once this is confirmed, it's basically set in stone. Irreversible.
Okay, but she only spent 0.01 out of 0.1 euro. What happens to the rest?
Good question. Her wallet creates another output in the same transaction. This sends the remaining Bitcoin, minus that transaction fee we mentioned, back to Alice.
To her own address.
Usually to a new address her wallet generates just for this purpose. It's called a change address.
Ah, for privacy. So people can't easily track all her spending back to one address?
Exactly. It's like getting change back in different bills and putting them in a different pocket.
Cool. So it's not like spending from a single account balance, more like combining and splitting specific digital coins.
That's a good way to think about it.
Yeah.
And if you're curious, the book actually gives an example transaction ID for early coffee purchase people can look up on a block explorer.
Oh, neat. We can maybe put that in the notes.
Mm-hmm.
So Alice's wallet builds this transaction, signs it digitally, then what?
Then it broadcasts it out to the Bitcoin network, like shouting it out to all the connected computers, the peers.
Hey, everyone. Alice wants to send Bob some Bitcoin.
Pretty much, it spreads really quickly across this peer-to-peer network.
But just broadcasting it doesn't make it official, right? Anyone could just shout anything.
Exactly. That broadcasted transaction is just pending. Proposed. To make it official, permanent, and verified, that's where mining and the blockchain come in.
Okay, let's dig into mining then. What is it actually doing?
So Bitcoin mining is done by specialized computers, the miners. They listen for these broadcasted transactions, gather them up.
The pending ones.
Yeah, the valid pending ones. They group them into what's called a block, and then they work to add this block to the official ledger, the blockchain.
And this process does two things, right?
Two critical things. First, it validates the transactions, making sure Alice actually had the Bitcoin to send, that she wasn't trying to spend the same coin twice, things like that. It enforces the rules.
Okay, security. And the second thing?
It's also how new Bitcoin are created. It's the only way new coins enter the system.
Ah, the reward for the miner.
Exactly. But it's a controlled process.
Right.
The Bitcoin code itself dictates how many new Bitcoin are created per block, and that amount gets cut in half roughly every 4 years.
The famous halving.
Yep. And there's a hard cap. Only about 21 million Bitcoin will ever exist. So it's designed to be deflationary over the long run, unlike, regular currencies where governments can just print more.
Okay, so miners gather transactions, put them in a block. How do they actually add it to the chain? You mentioned it's competitive.
Highly competitive. They're all racing to solve a really hard computational puzzle. It's called proof of work, or POW.
Proof of work? What kind of puzzle?
It involves taking the block data, plus some other information, including a reference to the previous block's unique ID, and running it through a specific cryptographic hashing function, SHA-256, over and over again.
Just trying different inputs.
Essentially, yes. They tweak a small piece of data called a nonce each time, generating a new hash output. They keep doing this billions, trillions of times per second.
Wow.
Until one miner somewhere in the world finds a hash output that meets a very specific, difficult target. Basically, a hash that starts with a certain number of zeros.
So it's like a lottery, but based on computing power.
Kind of. The more computing power you have, the more guesses you can make per second, the higher your chance of finding the solution first. And the amount of power on the network now is just astronomical.
Right, I've heard it uses a lot of electricity.
It absolutely does. That energy expenditure is what fundamentally secures the network.
Okay.
It makes it incredibly expensive for anyone to try and cheat the system.
Okay, so a miner finds the winning hash. What happens then?
They finalize their block. They include all the transactions they gathered, usually picking the ones with the highest fees first.
Ah, the incentive again?
Yep. And they add a special transaction, the Coinbase transaction. That's where they pay themselves the block reward, the newly created Bitcoin, plus all the transaction fees from that block.
Nice work if you can get it.
Yeah. And crucially, this new block contains the hash, that unique digital fingerprint of the previous block in the chain.
Connecting it back, like a chain link.
Exactly. Think of it like stacking Lego bricks. Each new block clicks securely onto the one before it because it references it cryptographically.
Okay, block created. Then,
The winning miner broadcasts their completed block to the network.
just like the transaction we broadcast earlier.
Right. Now, all the other miners receive this block. They quickly check two things. Is the proof of work solution valid? And are all the transactions inside the block valid according to Bitcoin's rules?
So they double check the winner's work.
They do. If it all checks out, they accept this new block as the latest addition to the chain. And then they immediately start working on the next block, building on top of the one they just validated.
So by building on top of it, they're kind of voting for it, agreeing it's the legitimate next step.
That's a perfect way to put it. They extend the chain. And that chain of blocks all linked together cryptographically back to the very first one, the Genesis block that is the blockchain.
The distributed ledger.
Yeah.
Shared by everyone. Immutable.
Immutable, ordered, transparent. It's this shared history book that everyone agrees on because of the computational work and the consensus rules.
Okay, that clarifies the mining and blockchain part a lot. So let's zoom in on some of the building blocks you mentioned. Addresses, keys.
Right, fundamental concepts. Let's start with a Bitcoin address. That's what you give someone so they can send you Bitcoin.
Like an account number.
Sort of, but more like the pay to line on a check, as Andreas puts it. It's derived from your public key using hashing.
Hashing again. So it's a fingerprint of the public key.
A digital fingerprint, yeah. And interestingly, an address doesn't always just represent one public key. It can sometimes represent a more complex set of rules, a script for how the money can be spent.
We'll probably get the scripts later, but these addresses, they look like random letters and numbers, often starting with a 1 or a 3.
That's right, usually 1 or 3 on the main network. That format uses something called base 5/8 check encoding.
Base 5/8. Check.
Yeah, it makes them a bit shorter, easier to handle than raw binary data. And this is the clever part. It includes a checksum.
Like for error detection.
Exactly. If you mistype even one character, the checksum likely won't match, and the wallet software will say, hey, this address is invalid. Helps prevent sending coins into the void.
Smart. Okay, so addresses come from public keys. What about private keys?
The private key. This is the most important piece. It's basically just a very large, randomly generated number, 256 bits.
How random.
Used to be cryptographically securely random. Andreas jokes you can flip a fair coin 256 times, but realistically you use a secure random number generator. The key point is, keep it secret. Keep it safe.
Because the private key is what lets you spend Bitcoin.
Precisely. It's the authority. Like the signature on the check, or maybe even better, the actual key to the vault. Lose it or let someone else get it, and they control your funds.
Okay. Secret private key? Then the public key.
The public key is mathematically derived from the private key. It uses something called elliptic curve cryptography specifically, a curve named SECP 256K1 for Bitcoin.
Elliptic curves. Sounds complicated.
The math is definitely advanced, but the crucial property is that it's a one-way street. You can easily calculate the public key if you have the private key.
But you can't go backwards. Can't figure out the private key just by looking at the public key.
Computationally infeasible. It would take, longer than the age of the universe with current computers. That one-way function is core to the security.
Okay, so private key generates public key gets hashed to make the address.
Mostly, yeah. There's a detail about compressed public keys, too. They store less data, but represent the same point on the curve.
Does that matter much?
Only in that a compressed public key and an uncompressed one, even though they come from the same private key, will generate different Bitcoin addresses, something to be aware of.
Huh, okay. And is there a standard way to write down or store these private keys?
Yes, there's the wallet import format, or WYFF. It's a base 58 check encoded version of your private key. Makes it a bit easier to copy or backup compared to just raw numbers.
Gotcha. Which brings us nicely to wallets. How do we manage all these keys?
Good transition. So early Bitcoin wallets were often pretty basic. They just generated private keys randomly, one by one, as needed.
Like a shoebox full of keys?
Kind of. They're called non-deterministic wallets. The big problem was backups. You had to save every single private key you ever generated. If your computer died and you hadn't backed up that one key, poof, those coins were gone.
Ouch. Sounds stressful.
It really was. That's why the development of deterministic, or hierarchical deterministic, HD wallets was such a breakthrough.
HD wallets, what's different?
With an HD wallet, everything starts from one single master secret, called the seed.
The seed.
Yeah, it's usually generated from a random source. From this one seed, the wallet can derive a practically infinite tree structure of private keys, public keys, and addresses, all in a predictable, deterministic way.
Deterministic meaning if you start with the same seed, you always get the same keys.
Exactly. So what's the huge advantage?
You only need to back up one thing. The seed?
Precisely. Back up that seed securely, and you can restore your entire wallet, all past and future keys and addresses, on any compatible wallet software or device. Huge improvement for usability and safety.
How does it derive all those keys from just one seed?
It uses a process called child key derivation, or CKD. It combines the parent key, starting with the seed, something called a chain code for added randomness, and an index number to generate each child key.
Okay, don't need all the math, but the concept makes sense. Master key creates branches of keys.
That's the idea. And how do you usually back up that all-important seed, not as a giant number?
Right, you see those lists of words.
Exactly. Mnemonic codes, usually based on a standard called BIP39. The seed is converted into a sequence of typically 12 or 24 common English words.
Like apple, table, river, happy, whatever.
Yep. Much easier for a human to write down accurately and store safely than a long string of random characters.
And I've heard about adding a passphrase, too.
You can, yeah. BIP39 allows an optional passphrase. If you use one, it's combined with the mnemonic words to create a totally different seed and therefore a different wallet. Adds another layer of security. Even if someone finds your words, they still need the passphrase.
Clever. Okay, so wallets manage keys derived from seeds. Let's quickly loop back to UTXO's unspent transaction outputs. You said they're like the coins?
Yeah, they're fundamental to how Bitcoin actually tracks value. When you receive Bitcoin, it sits there as a specific UTXO linked to your address. When you send Bitcoin, your wallet consumes one or more of your UTXOs as inputs.
And creates new UTXOs as outputs for the recipient and for your chain.
Exactly. So the set of all UTXOs across the entire network at any given moment represents the current state of all spendable Bitcoin. Who owns what, essentially? It's this constantly updated pool of spendable chunks.
And that's how it prevents double spending, because once a UTXO is spent as an input, it's consumed and can't be spent again.
Precisely. The miners validating transactions check that the inputs, the UTXOs being spent, are actually in that current spendable pool and haven't already been spent.
Okay, that ties a lot together. Inputs, outputs, UTXOs, fees.
Right. And maybe we can touch on some slightly more advanced transaction features now, like fees and scripts.
Yeah, let's do that. We mentioned fees are the difference between inputs and outputs. How are they set?
Well, You, or typically your wallet software, decide how much of a fee to include. It's implied, not explicitly stated, as fee equals X, the higher the fee you attach.
The more attractive your transaction looks to a miner trying to fill a block.
Exactly. Especially when the network is busy, if you set a very low fee, your transaction might sit unconfirmed for a long time, maybe hours or even days. So the fee acts like a priority mechanism.
Pay more, get processed faster, market dynamics.
Pretty much. Now, another cool feature is pay-to-script hash, or P2SH.
P2SH. Sounds technical.
It sounds it, but the idea is to simplify things. Imagine a company, like Mohammed's example in the book, that wants extra security. They set up a multi-signature account.
Meaning multiple people need to sign off to spend the funds.
Right. Maybe 2 out of 3 directors need to provide their digital signatures. Now, the actual Bitcoin script to enforce that rule can be kind of long and complex.
Yeah.
Instead of making every customer who pays them deal with that long script, P2SH lets the company create a hash of that script.
Like a fingerprint of the rules.
Exactly. And they give out an address based on that hash. These are the addresses that usually start with a 3.
So the sender just sends to this simple 3 address.
Yep. Much easier for the sender. Then, when the company wants to spend those funds later, they provide the original script and the required signatures for a G 2 out of 3.
So it hides the complexity until it's actually needed.
Precisely. Keeps things neat on the sender's side and often makes the initial transaction smaller on the blockchain.
Smart. What else? Time locks.
Time locks. Also very powerful. They basically let you restrict when Bitcoin can be spent.
Like post-dating a check?
That's a great analogy for one type and lock time.
Yeah.
It's set at the transaction level and says, this whole transaction is invalid until block X or time Y.
Okay. What other types are there?
There's also check lock time verify, or CLTV. This is an instruction inside a script applied to a specific output. It says, this particular chunk of Bitcoin cannot be spent until time Y or block X.
So you could lock up funds for a specific duration?
Exactly. Think about things like maybe inheritance planning or complex financial contracts or funds held in escrow that only become available after a certain date.
Interesting. And you mentioned relative time locks, too.
Yeah, things like in sequence and check sequence verify. These specify a delay relative to when the output itself was confirmed on the blockchain. So wait 100 blocks after this transaction gets confirmed before this output can be spent.
So absolute time versus relative time, lots of flexibility there for building more complex arrangements.
Definitely. These scripting capabilities, including time locks and multisig, show that Bitcoin was designed with more than just simple payments in mind. It's programmable money.
Which leads nicely into thinking about applications beyond just currency, right?
Absolutely. Because the underlying blockchain technology, with its security, its timestamping, its global replication, it has properties useful for many other things.
Like what? What are the key properties?
Well, it's neutral. No single entity controls it. It provides secure timestamping, proving something existed at a certain time. It's replicated everywhere, making data resilient. It's forgery resistant. And it provides consistency. Everyone sees the same history.
Okay, so how have people tried to use those properties?
An early idea was colored coins.
Colored coins, like painting Bitcoin.
Yeah, sort of conceptually. The idea was to take a tiny amount of Bitcoin, like a single Satoshi, the smallest unit, and digitally tag or color it to represent something else.
Represent what?
Anything, really. A share of stock, ownership of a physical item like a car, a concert ticket, a digital collectible.
So the Satoshi acts like a token or a voucher for the other asset.
Exactly. You'd issue these colored coins, and then you could trade them using standard Bitcoin transactions. The blockchain would track the ownership of the color, which represented the real-world asset.
Did that take off?
It was more of an early experiment, showed the potential, but it had limitations. For one, standard Bitcoin wallets and explorers wouldn't necessarily understand or display the color. They'd just see a tiny Bitcoin transaction.
Right. But it proved the concept the blockchain could be a general-purpose ledger.
It did. And building on that, we now see more sophisticated approaches, particularly for scalability, like payment channels and state channels.
Okay, what's the core idea there?
The core idea is to handle lots of transactions off the main Bitcoin blockchain.
Off-chain. How does that work securely?
Well, 2 or more parties lock some funds on the main blockchain into a special multi-signature address. Then they can exchange updated balances between themselves privately, signing transactions but not broadcasting them immediately.
Like running a tab?
Exactly like running a tab. They can make hundreds or thousands of payments back and forth off-chain, just keeping track of the latest balance sheet signed by both parties.
And only when they want to settle up.
Do they broadcast the final state the net result of all those off-chain transactions to the main Bitcoin blockchain.
Ah, so you avoid cluttering the main chain with every single tiny payment.
Precisely. It dramatically increases the potential transaction throughput and lowers fees for those interactions.
And the Lightning Network is the big example of this.
Yes, the Lightning Network is the most well-known implementation of payment channels on Bitcoin. It allows for near-instant, very low-cost payments, which is great for things like micropayments or everyday purchases.
So Bitcoin's tech enables much more than just sending BTC from A to B, colored coins, payment channels. It's a platform.
It really is. But all these applications, all this innovation, still fundamentally rely on the security of that base layer, the Bitcoin blockchain itself.
Which brings us back to decentralization.
Absolutely. That's the bedrock. Unlike traditional finance, with its central banks and intermediaries who control access and reverse transactions.
Bitcoin puts the trust in the network protocol, the math, and the distributed consensus.
Right. Security comes from the massive proof of work, the transparency of the ledger, and the fact that no single entity can easily change the rules or censor transactions. The responsibility shifts.
To the user.
Largely, yes. It shifts responsibility to you to manage your private keys securely. If you control your keys, you control your Bitcoin. If you give your keys to someone else or use services that hold them for you.
You're trusting them, not the Bitcoin protocol itself.
Exactly. And conducting transactions entirely off-chain without the right cryptographic guarantees can also sidestep the core security model. So understanding how it works helps you use it safely.
It all comes back to those core principles. Okay, so wrapping this deep dive up. We started with leafcutter ants.
Simple rules, complex emergent system.
And Bitcoin, with its relatively simple rules for transactions, blocks, and consensus, creates this incredibly powerful, secure, decentralized network for value.
Hopefully understanding these pieces, inputs, outputs, UTXOs, mining, the blockchain keys, wallets, even things like P2SH and time locks gives you a much clearer picture.
Yeah, a solid foundation for making sense of crypto and blockchain tech generally.
Yeah, that's the goal.
So here's a final thought to leave you with. We've seen Bitcoin used for currency, for representing other assets, for faster payments, but given its core properties, that neutrality, the security, the immutability,
Yeah.
what else could it be used for?
Good question.
What applications haven't we even thought of yet? What other kinds of assets or agreements could be managed securely and transparently on a global, decentralized, trustless ledger like this? Something to ponder.